Welcome back to the deep dive. Today, we're focusing squarely on BYD,
Right.
but we're not talking about their massive battery business, which, let's be honest, everyone knows about.
Yeah, that story's been told.
We're looking much closer at something else, at the sophisticated dynamic brain of the electric vehicle, the motor itself.
That's absolutely right. And our sources today are pretty technical.
Very technical.
We have a stack of recently published patent applications straight from the China National Intellectual Property Administration, CNIPA.
Okay.
And these documents, they really reveal BYD's long-term play. They're detailing the technical architecture for an entirely new generation of electric motors.
Specifically, we are diving deep into what they call the Variable-Flux permanent magnet synchronous motor, or VF-PMSM for short.
It sounds complicated.
It does, but the goal behind it is actually really elegant.
And our mission for you, the listener, is to kind of pull back the curtain on this. We need to understand the fundamental physics that limits really every traditional EV motor today. And then we can analyze exactly how BYD's variable flux tech aims to dynamically adjust the motor's operation to the driving conditions instead of the other way around.
That's the key. That's the leverage point. This isn't just some marginal spec bump.
No, not at all.
This is about unlocking significant additional driving range without adding a single pound of weight or cost to the battery pack.
And that is the enormous prize waiting at the end of this.
Exactly.
Yeah.
Okay, so let's unpack the core compromise they're trying to solve. If you've driven an EV, you know that immediate burst of torque right off the line.
Oh, yeah, it's addictive.
That feeling is addictive, and it comes from maximizing the magnetic field. It's perfect for, like, the urban commute.
Yeah.
Stop-and-go traffic.
Right. But that low-speed brilliance, it comes with a high-speed penalty. And that's the conflict.
That's the compromise.
It's the inherent weakness of what we call the conventional permanent magnet synchronous motor, or PMSM. Our sources really emphasize that the core issue is that these motors use a fixed rotor magnetic flux.
Meaning the strength of the magnets never changes.
It never changes. The magnetic field generated by the permanent magnets on the rotor is constant.
And at first, that sounds like a good thing, right? A strong, consistent field means consistent power.
For getting off the line, yes. That fixed maximized flux delivers maximum torque. But here's the unavoidable physics trade-off. When the rotor starts spinning really quickly...
Back on the highway.
Exactly. Think sustained highway cruising. That fixed magnetic field begins generating a significant counter-electromotive force. We just call it back EMF.
So the motor becomes its own worst enemy. It's generating a voltage that actively fights the direction you're trying to push it.
You've got it. It's essentially trying to slow itself down. So when you force current into the windings to overcome that back EMF and maintain speed, the electrical energy you need just skyrockets.
The motor is basically operating outside its comfort zone.
Way outside. It's out of its narrow efficiency sweet spot, and it's just rapidly shedding energy as heat. I mean, a motor that's 95% efficient in the city might plummet to 85% or even lower at highway speeds.
And that efficiency drop, losing 10% of your power, that's just incredibly painful for range.
It's a killer.
When you're driving at 70 miles per hour, you're draining the battery so much faster than you'd expect based on the car's, standard rating.
It creates this fundamental design headache. Manufacturers have to compromise. They either design for torque, which means great city performance but poor highway range.
Or they design for high-speed efficiency, and you get lousy acceleration.
Right. And to mask this, a lot of them just have to install a heavier, more complex, and more costly battery pack just to make up for the wasted energy.
Okay, so if the fixed flux of the permanent magnet is the root cause of this whole trade-off, then the solution has to be dynamic magnetic flux control.
That is the core innovation BYD is chasing here. The whole principle is to dynamically adjust the rotor magnetic flux based on what you actually need in that moment.
Right. Why run a constant maximum field if you only need that strength for a second, for instant torque? This makes the motor adaptable. It's almost like, it feels like the same leap that variable valve timing was for gasoline engines.
It's a perfect analogy. It really is. It shows that adaptable physics is the future. Let's look at the two key states of the VF-PMSM as they lay it out in the filings.
Okay, take us through low speed first.
At low speeds, when you want that instant high torque-like pulling away from a light, the flux is maximized. It's elevated to make sure you have high pulling power.
So it's acting just like a normal motor in its happy place.
Exactly. Performance is maintained. But here's the critical difference. When the rotor hits those high rotation speeds,
The highway cruising part.
right, the motor controller actively reduces or limits that magnetic flux. By managing the field strength downward, you directly lower that back EMF voltage.
So you're deliberately choosing to accept less absolute magnetic force. But by doing that, you drastically reduce the internal resistance fighting the electricity.
Precisely. You are swapping a tiny amount of field strength for a huge gain in electrical efficiency. You stop dumping all that electricity into just overcoming the counterforces.
And the result, according to the patents,
Oh.
is what?
A dramatic extension of the high-efficiency operating zone. It works efficiently over a much, much wider range of speeds. This means reduced losses at high speeds and optimized torque delivery across the board.
All without needing that bigger, heavier battery pack.
That's the goal.
And the sources also mention some other benefits, right? Like improved thermal stability.
They do. I mean, it makes sense. If you're losing less energy to these counterforces, you're generating less waste heat.
Which simplifies your cooling systems, improves the life of the components. It feels like a win-win for the whole system.
It is. This moves the whole EV engineering conversation away from just battery capacity. It's about total system efficiency, maximizing the work you get done per kilowatt hour.
Okay, we've established the why, the necessity of this variable flux. Now we get to the really intricate part, the engineering.
The how.
The how. And the sources show BYD isn't just betting on one single idea. They've filed 4 distinct patent applications, each one outlining a unique mechanical architecture to achieve this.
It really does. It shows the sheer scale of their R&D commitment. This is an exhaustive exploration of the design space.
And all filed recently.
Yeah, these 4 were filed in May 2024, and they detail entirely different ways to physically manipulate the magnetic field inside the motor. Let's dive into them.
Let's do it. Let's start with the approach that looks sort of beyond the motor itself.
Okay, that would be the first key patent, the integrated component approach. This design is all about a flux adjustment component that's integrated not just with the motor, but specifically with the transmission or the drive system.
What's the implication of that, integrating it with the transmission?
It signals a focus on coordinated powertrain management. So instead of the motor just adjusting its flux in a vacuum, this approach makes the motor and the gearbox talk to each other constantly.
So the system anticipates the torque you'll need and the speed change at the same time.
Exactly. It adjusts the magnetic field accordingly, optimizing the entire mechanical chain in real time. It's a holistic approach.
Which makes perfect sense for a company that builds the entire vehicle, from the ground up. What's the next method?
The second is what we can call the movable magnet element approach. This one describes a mechanical element that is physically mobile relative to the permanent rotor magnets.
Okay, so you've got moving parts inside the motor.
Yes. Imagine internal magnetic shields, or maybe flux shunts, that can physically shift their position.
So you're not changing the magnet itself, but you're physically controlling where the magnetic field lines go. You could shunt them away from the stator coils at high speed.
Precisely. By displacement, just physically moving this regulating element, they can expand or restrict the effective magnetic field that the motor windings see.
That requires incredible precision, I imagine.
Oh, absolutely. Mechanical and electrical control have to be perfect, but it offers a very direct, tangible way to regulate the field strength just by changing the internal geometry.
It's complex, but the benefit of a truly adaptable field must be worth it in their view. Okay, let's move to the third approach. This one focuses on a different dimension of control.
Right, that's the axial adjustment mechanism. Most magnetic flux is thought of radially, how the field interacts around the circumference. This patent details an assembly that can modify the flux along the rotor's axis.
Down the length of the motor. That sounds fundamentally different. What does that solve?
It could solve issues of uniformity and compact design. By adjusting the magnetic circuit down the rotor's length, they can potentially get finer tuning of the response, or maybe integrate the whole thing into a more compact longitudinal design.
And space is always a premium in a car.
Always. This shows they're really exploring three-dimensional flux manipulation. It's very deep stuff.
Okay. And finally, the fourth patent.
The fourth is the radial variation configuration. This one focuses on a design that adjusts the radial area of a magnetic conductive part.
So not moving a shield, but actually changing the size of the pathway the magnetic field passes through.
Yes, think of it like adjusting the aperture on a camera lens, but for magnetism.
Wow.
This allows for incredibly fine-grained, instantaneous control of the internal flux. It probably offers the best responsiveness for rapid changes in acceleration or load.
So you're maximizing efficiency even during micro adjustments in your driving.
That seems to be the idea.
Okay, let me just recap. We have 4 distinct, complex engineering paths here: an integrated system, a movable physical shield, an axial length adjustment, and a radial area variation. They all have the same goal: make the motor intelligent and adaptable. But the diverse architectures, it just shows this is not a hopeful punt on one idea.
No, it's a systematic R&D effort to just dominate this technological space.
And this is just what's been published.
Right. And if we connect this to the broader context, these 4 patents are just the tip of the iceberg. Our sources confirm BYD has been filing numerous other patents all year.
On what?
On optimized motor structures, new rotor designs, stators, complex flux management systems, the works.
This tells us their long-term vision isn't just about plugging this tech into existing motors. They're potentially designing entirely new systems around this capability.
Precisely. It's a deep industrial vision centered on component efficiency, not just scaling up the battery.
Which brings us to the critical question. When does this go from paper to road? What's the current status?
Well, right now, these are protected technical solutions and declared goals. Things like reduced losses, extended efficiency, but we have no public confirmation of commercial deployment.
No validated third-party results yet.
Not for these specific VF-PMSM technologies, no. The journey from a patent schematic that proves a concept to a reliable, cost-controlled, mass-produced component is, well, it's always the hardest hurdle.
So what does this aggressive patent strategy signal for the rest of us and the broader EV market?
It means the fundamental efficiency battle is heating up. The battery is the energy reservoir, sure, but the motor is rapidly evolving into the dynamic brain that dictates how far that energy can actually take you.
And BYD is investing heavily to make that brain intelligent.
Exactly. Free from the limitations of fixed flux physics, this is serious competition in efficiency, which ultimately translates directly into better range and lower vehicle cost, especially in the mid-market where every kilowatt hour saved is paramount.
And that is massive for the ownership experience, making every drive more predictable, more efficient.
Yep.
So we've broken down the central engineering challenge of back EMF, the huge potential of variable-flux tech, and we've seen 4 distinct, intricate ways BYD is trying to solve it.
Yeah.
It really does signal a foundational shift.
And that leaves us with a final provocative thought for you to mull over.
Okay.
If motors can intelligently adjust their magnetic flux as seamlessly as breathing, based on load and speed, what other systems in the EV could suddenly become obsolete?
What do you mean?
Well, think about the currently heavy, oversized cooling requirements for motors, or the restrictive gear ratios that are necessary today. This VF technology could potentially trigger a complete, system-wide redesign focused on lightweighting everything else.
A cascade of optimizations. That's a great point. Thank you for joining us on this deep dive into the technical heart of the next generation of EVs. We really concentrated today on presenting these complex sources clearly and comprehensively.
So you could quickly grasp the engineering strategy here.
Exactly. If you enjoyed understanding how these intricate concepts might fundamentally change EV performance, be sure to follow the channel for more curated knowledge shortcuts. We'll be back soon with another deep dive.